and thank you for tuning into this presentation. My name is John Templeton. I'm a postdoctoral researcher at Florida International University in the Mosaic Lab within the Knight Foundation School of Computing and Information Sciences. The title of the talk that I will be presenting on behalf of all authors, is Using Wearable Devices to Mitigate Bias in Patient-Reported Outcomes for Aging Populations. In this presentation, first, the motivations for this work will be addressed, followed by a brief introduction and related works of current versions of clinical assessments. Next, the methodology for participant recruitment, subsequent data collections, and data processing will be covered. Then, the results of patient-reported outcome analysis and digital outcome measures will be shown, followed by a discussion of the future of clinical outcome assessments, limitations of this study, and future works. Finally, a brief set of conclusions will be presented. There are two main motivations of the work presented in this study. First of which is to assess the variability of an individual's perceived functionality for neurocognitive functions, such as autonomic function and sleep, as well as activity levels across aging populations in comparison to objective physiological measures collected using wearable device sensors. Second is the assessment of disparities between healthy aging populations and individuals with confirmed neurodegenerative diseases, such as individuals with Parkinson's disease. These motivations can better be understood with the inclusion of background knowledge on clinical neurological assessment systems. Typically, as an aging individual is suspected of having a progressive or acquired neurological condition, a cognitive screening assessment is given. These screening assessments typically include patient-reported outcome questionnaires in which individuals subjectively rank their capacity across different functional areas of neurocognition. These functional areas of neurocognition include motor, memory, speech, language, behavior, sensory, sleep, executive function, and autonomic functions. Examples of patient-reported outcome questionnaires specific to this work regard areas of sleep, autonomic function, and motor function as it relates to physical activity. These questionnaires include the Sleep Quality Scale, Borg Rating Scale, which is a rating of perceived exertion, an Exercise Self-Efficacy Scale, and the PDQ-39, which is a Parkinson's disease-specific questionnaire regarding a patient's overall quality of life. However, while these patient-reported outcomes are commonly used to monitor a patient's thoughts or opinions with respect to short-term changes like day-to-day, as individuals age, their perceived neurocognitive functionalities for motor, sleep, and autonomic functions may become reliant on changes in their cognitive processes, their memory of past exercise experiences, as well as felt experiences in the body. Further, as these individuals age, there exists an increased susceptibility to certain neurodegenerative diseases, including Parkinson's disease, that may affect changes in the way individuals perceive their neurocognitive functionalities. This concept is expressed further using the stereotype embodiment theory, which suggests that beliefs surrounding culture lead to self-definitions that may influence the perceived functioning and health, such that if you are deemed healthy, you embody the perceived notion that you are comprehensively healthy, and vice versa. As a result, the aim of digital health technology should be used to combine these responses with objective data to yield higher diagnostic and prognostic values, while also reducing individual variability and/or bias. This is possible as digital health technology, including smartphones and wearables being the main focus of this current work, provide users the capability to expand functional assessments with more fine-grained longitudinal analysis, allowing for objective scoring, the interpretation of results relating to possible disease diagnoses, and the subsequent monitoring of disease progression. These wearable devices are able to provide a focus on multiple functional areas of neurocognition, including autonomic functions like breathing and heart rate, and sleep, in addition to their ability to collect commonly used metrics like activity data. The methodology section for this work will also be used to give a better understanding of current patient-reported outcome assessments and digital outcome measures as related to the previous material covered. In this pilot study, 30 adults participated who were between the ages of 50 and 85. These participants consisted of two groups, those with a confirmed diagnosis of Parkinson's disease, as well as age-matched healthy controls. This work focused on individuals with Parkinson's disease, as it is a common neurodegenerative disease that affects multiple functional areas of neurocognition, in addition to the ability to complete functional exercise activities. All participants were required to complete a set of questions commonly administered in clinical settings for aging populations, as well as a specific quality of life questionnaire. These questionnaires were administered to accompany and confirm diagnoses provided by medical practitioners. In addition, all participants were required to complete daily patient-reported outcome questionnaires and wear a wearable smart tracker device, the Fitbit Charge 5, for the 4-week duration of this study. All participant-reported outcome questionnaires were scheduled, where participants were alerted using push notifications for the completion of a mobile-based daily health questionnaire. These were scheduled at the end of each day, e.g. before bed, such that all responses were related to the previous 24 hours. Questions regarding sleep quality, breathing capacity, perceived exertion, and activity, as well as the confounding factors of each, were asked and are depicted in the table presented. For the wearable device, all participants wore it on their non-dominant hand continuously for the duration of this study, only taking the smart tracker off to charge. Individuals were instructed to charge the device daily when they were sedentary or inactive, but not sleeping, as the collection of sleep data was imperative to the outcomes of this work. Given inherent device sensors, including the device accelerometer and optical sensors, the collection of physical activity, sleep, heart rate, and breathing features were able to be computed, such as sleep quality, step count, caloric burn, metabolic rate, and activity levels. As collected feature values and patient-reported outcome responses are of each a unique type and come from standardized questionnaires and tools with varying ranges and units, feature normalization is necessary. For the feature normalization of this work, z-scores were used. The calculation of a z-score is depicted in the presented equation where x is an individual's score, mu is the population mean, and sigma is the standard deviation of the population. This z-score is measured in terms of standard deviations from the mean, such that if a z-score is 0, it indicates that the data point score is identical to the mean, whereas a z-score of 1 would indicate a value that is 1 standard deviation from the mean. These z-scores may be positive or negative, with a positive value indicating a score above the mean and negative indicating a score below the mean. Following this feature normalization, both perceived and sensor-based aggregated scores can be formed for analysis. The next set of slides will explore the results of this work, both in terms of patient-reported outcome analysis and digital outcome measures for use in bias mitigation. All normalized perceived and sensor-based scores were analyzed between individuals with Parkinson's disease and healthy age-matched controls using statistical methods like ANOVA and post-hoc t-tests. Normalized data for patient-reported outcomes presents that, on average, age-matched healthy control populations have significantly higher functionality scores, with a p-value much less than 0.01, across all collected patient-reported outcomes, including how the individual feels in general, their overall sleep quality, autonomic functions of breathing and heart rate, as well as their physical activity when compared to individuals with confirmed diagnoses of Parkinson's disease. This is confirmed via the use of digital outcome measures, as on average, age-matched healthy control populations have higher functionality for sensor-based scores across all areas when compared to individuals with confirmed diagnosis of Parkinson's disease. This concept is further depicted in part using the stereotype embodiment theory, which suggests again that one's beliefs surrounding culture leads to self-definitions that may influence perceived functionality related to health, such that if you are deemed healthy, you embody the perceived notion that you are comprehensively healthy, and vice versa. This perspective is observed in the presented figure as the Parkinson's disease population overall perceived scores for sleep quality, heart rate, and physical activity are significantly lower than sensor based normalized values, with a p value of 0.018, 0.009, and 0.007, respectively. Whereas conversely, the age matched healthy control population's overall perceived scores across all functions, sleep, breathing, heart rate, and physical activity, are higher than sensor based normalized values, where sleep and heart rate are significantly higher, with a p value of 0.002 and 0.012, respectively. It is noted that the Parkinson's disease population overall perceived score for breathing is higher than the sensor based normalized values as depicted in the presented figure. However, it is also expressed that there is not a significant difference between these scores given the population. The following slides will discuss the limitations and future work completed, in addition to the future of clinical outcome assessments for aging populations. A major limitation of this pilot study arises given the population size and breakdown. Future work in this domain should include the collection of much larger data sets of these populations, in addition to populations across more neurodegenerative diseases, such as Alzheimer's disease, ALS, multiple sclerosis, Huntington's disease, and other types of dementia, as well as their stages. This would allow for the separation of individuals based on disease presence as well as their respective stage for a more fine-grained classification approach. This is necessary for both the assessment of perceived functionality and sensor-based scores as they relate to representative aging populations. Further, this work only explores a subset of neurocognitive functions as they relate to digital health technologies. Additional work with respect to wearable devices, utilizing electrodermal activity sensors for the assessment of stress and behavior, would expand wearable monitoring efforts to include more functional areas of neurocognition. In addition, expanding this work to include additional IoT devices, such as smartphones and tablets, and their inherent sensors and capabilities, would also allow for the expanded digital outcome measures of more functional areas of neurocognition, such as memory, speech, language, sensory function, executive function, and behavior. With the introduction of these additional IoT devices for the subsequent collection of novel digital features, data fusion techniques will be a high area of importance as the new feature set will contain many more relevant digital outcome measures in addition to the patient-reported outcomes. These data fusion techniques will be necessary to provide clinicians with functional indicators of each area of neurocognition with respect to diagnosis, monitoring, and prognosis efforts. As a result of the expanded data collections, using additional IoT devices and device capabilities for the collection of additional functional areas of neurocognition, clinical outcome assessments, which combine patient-reported outcomes and digital outcome measures, will allow for the further objective, fine-grained longitudinal analysis of symptom-specific functions. The collected data from these digital health assessments would then be able to expand current clinical staging methods, intervention recommendations, and monitoring the evolution of disease over time through the formulation of health indicators, threshold values, and decision programs. In turn, this will allow for higher accuracy of clinical diagnosis, higher personalization of interventional protocols, and an improved quality of life. In conclusion, the aim of digital health systems should be to increase the reliability and accuracy of patient-reported outcomes by combining it with objective digital outcome measures from mobile-based devices. As wearable devices allow for the objective feature collection, both opportunistically and longitudinally, they may be used to help assess disparities between healthy aging populations and those with confirmed neurodegenerative diseases. This pilot study was completed to give an initial understanding of how patient reported outcomes differ from digitally collected features from wearable devices, specifically in the case of Parkinson's disease. Ultimately, however, the integration of these digitally collected features, in addition to patient reported outcomes, will enhance the understanding of how neurological diseases present and provide necessary personalized diagnostic and monitoring information. I would like to take this opportunity to acknowledge my professional and institutional collaborators listed here. A short list of references has been provided for the purposes of this presentation. However, for the complete list of references, please refer to the corresponding paper in the upcoming conference proceedings. I would also like to take this opportunity on behalf of myself and all other authors of this work to thank you for your time and listening to the presentation entitled Using Wearable Devices to Mitigate Bias in Patient-Reported Outcomes for Aging Populations. If there are any questions, please feel free to contact us.